The topic of the video is digitalization of project management, recent advances in methods, technologies, algorithms, programming and applications, emerging technologies and their importance to the world and human life. We are living through an extraordinary period of technological development. Artificial intelligence, AI, AI agents, machine learning, digital twins, robotics, autonomous systems, Internet of Things, IoT, cloud and edge computing, advanced data analytics, computer vision, quantum computing and AI-assisted software engineering are increasingly influencing almost every area of economic and social activity. These emerging technologies are important because they expand our capacity to analyze complex systems, automate repetitive activities, optimize scarce resources, predict future events and support better decisions. Their applications extend across engineering, construction, manufacturing, healthcare, finance, energy, transportation, water, agriculture, education, humanitarian operations, infrastructure and government. Project management is particularly important in this transformation because much of the world's economic, technological and infrastructure development is delivered through projects. Buildings, transport systems, renewable energy facilities, software systems, hospitals, manufacturing plants, research programs and major organizational transformations are all planned and implemented as projects. Therefore, improving project management can have effects far beyond individual projects. Better project management can mean lower costs, shorter delivery times, improved safety, better use of resources, greater sustainability and higher probability of achieving the intended economic and social benefits. Digitalization provides an opportunity to fundamentally redesign how projects are conceived, planned, executed, monitored and controlled. Digitalization of project management. Traditional project management is based on several fundamental activities: defining objectives, establishing scope, developing schedules, estimating costs, allocating resources, managing risks, coordinating stakeholders, monitoring performance and controlling changes. These principles remain important. What is changing is the technological environment in which they are performed. Traditional project management often depends on periodic reports, spreadsheets, meetings, manually updated schedules and the professional judgment of project managers. Information may be distributed across different departments, contractors and software systems. By the time a significant cost variance, schedule delay or resource problem appears in a formal report, the underlying problem may have existed for weeks. Digital project management creates a different operating model. Project information can increasingly be captured continuously from enterprise systems, sensors, mobile applications, cameras, drones, equipment, financial databases and digital platforms. Cloud systems can integrate these information streams. Algorithms can analyze them, and AI systems can identify patterns that may not be immediately visible to human managers. The management cycle therefore evolves from plan right pointing arrow, execute right pointing arrow, periodically measure right pointing arrow, correct towards, sense right pointing arrow, integrate right pointing arrow, analyze right pointing arrow, predict right pointing arrow, optimize right pointing arrow, decide right pointing arrow, act right pointing arrow, learn. This is a fundamental change. Project management becomes more dynamic, predictive and potentially autonomous. Recent advances in project management methods and models. Digitalization does not eliminate established project management methods. Instead, it strengthens them through data, algorithms and automation. Traditional techniques such as work breakdown structures, Gantt charts, critical path method, program evaluation and review technique, earned value management and resource scheduling remain valuable. However, they can now be connected to live project information. A digital work breakdown structure, for example, can be connected with cost databases, procurement information, schedules, engineering models and real-time progress data. Critical path calculations can be automatically updated when activity durations change. Earned value indicators can be displayed continuously through dashboards rather than calculated only for periodic reports. More advanced approaches include agile, lean, hybrid project management, systems engineering, model-based management and data-driven project control. Digital twins introduce another important model. Instead of managing a project only through documents and schedules, organizations can create digital representations of physical assets, processes and operations. These models can be continuously updated using real-world data. Project managers can therefore ask not simply, what happened, but increasingly, what is happening now? Why is it happening? What is likely to happen next? What should we do about it? These questions represent the progression from descriptive to diagnostic, predictive and prescriptive project analytics. Uncertainty and risk analytics. Every project operates under uncertainty. Costs may increase. Activities may take longer than expected. Equipment may fail. Suppliers may be delayed. Market conditions may change. Weather can disrupt construction. Regulations may change. Technical assumptions may prove incorrect. Digitalization enables these uncertainties to be analyzed more systematically. One important technique is Monte Carlo simulation. Instead of assigning a single fixed duration or cost to an uncertain activity, probability distributions can represent alternative possibilities. Thousands of simulated project scenarios can then be generated. The result may indicate, for example, that a project has a 70% probability of finishing within a particular budget or an 80% probability of meeting a particular completion date. This is much more informative than presenting one deterministic forecast. Modern risk analytics can combine Monte Carlo simulation with sensitivity analysis, Bayesian methods, machine learning and scenario modeling. AI can analyze historical project data to identify patterns associated with cost overruns, delays, contractual disputes or safety incidents. Risk management can consequently evolve from a largely periodic process into a continuously updated early warning system. Computer vision, robots, drones and reality capture. One of the most important developments in physical projects is the increasing ability to digitally observe the real world. Computer vision allows machines to interpret images and video. Deep learning algorithms can identify objects, people, equipment, materials, defects and activities. In construction and infrastructure projects, computer vision can support progress measurement, quality inspection and safety monitoring. Drones provide another valuable source of information. They can survey large sites, inspect difficult locations, monitor progress and produce high-resolution images. Photogrammetry can convert overlapping photographs into three-dimensional models. Laser scanning can produce highly accurate point clouds representing physical environments. This creates the possibility of comparing plan condition right pointing arrow actual condition. For example, a digital engineering model may show what should have been constructed by a particular date. Drone imagery or laser scanning can establish what has actually been constructed. Algorithms can compare the two. Robotics extends digitalization from observation to physical action. Robots can increasingly perform inspection, surveying, material handling, repetitive construction activities and maintenance. When robotics is connected with AI, computer vision and digital project systems, physical project execution itself becomes part of the digital management environment. Cloud computing, edge computing and project data platforms. A digital project may generate enormous quantities of information from schedules, costs, contracts, engineering models, sensors, images, procurement systems, equipment and communications. Cloud computing provides scalable infrastructure for storing, processing and sharing this information. Instead of project information being isolated on individual computers, cloud platforms allow authorized participants to work within shared digital environments. This supports collaboration among project managers, engineers, contractors, suppliers, consultants and clients. However, not every computation should occur in distant cloud infrastructure. Edge computing processes information close to where it is generated. Consider a camera monitoring a hazardous industrial site. Sending every video frame to the cloud before identifying a safety hazard could introduce unnecessary delay and bandwidth requirements. An edge device can analyze the video locally and generate an immediate warning. Hybrid architectures therefore combine edge intelligence plus cloud intelligence. Project data platforms increasingly integrate schedules, financial information, engineering data, documents, IoT streams and operational information. The result is potentially a unified digital project environment rather than a collection of disconnected applications. Programming for digital project management. Programming is becoming an increasingly valuable capability for engineers, project managers, and technical professionals. Commercial software remains important, but every organization has specialized requirements. Programming enables customized analytics, integration, and automation. Python has become particularly valuable because it supports data analysis, AI, machine learning, optimization, simulation, and automation. Python programs can automatically analyze schedule data, generate reports, forecast costs, optimize resources, or process sensor information. SQL provides powerful capabilities for managing and querying structured project databases. JavaScript and related web technologies support interactive dashboards and browser-based project applications. C and C++ remain important for high-performance applications, embedded systems, robotics, sensors, and real-time control. Application programming interfaces, or APIs, are equally important because they allow different software systems to communicate. A project management platform can potentially exchange information automatically with accounting software, engineering systems, procurement platforms, digital twins, and AI applications. Programming therefore provides the connective tissue of advanced digital project management. AI-assisted programming, coding, and software engineering. A particularly important recent development is AI-assisted programming. Generative AI systems can now help software developers and engineers generate code, explain programs, identify errors, create tests, produce documentation, and develop prototypes. This can significantly change the economics of developing specialized project management applications. A project engineer may describe a requirement such as: analyze this project's cost and schedule data, identify major variances, and generate a management dashboard. AI-assisted development tools can help translate such requirements into software. AI can also support requirements engineering, system architecture, database design, testing, debugging, and software maintenance. This does not eliminate the need for professional software engineering. AI-generated software must be tested and validated, particularly when applications affect safety, engineering decisions, contractual obligations, or major financial commitments. Nevertheless, AI-assisted programming can dramatically lower the barriers to developing customized digital project solutions. The distinction between a project manager who uses software and one who can help create intelligent project management systems may therefore become increasingly important. AI agents and multi-agent systems for project management. AI agents represent another major development. Traditional AI models generally receive an input and generate an output. An AI agent can potentially pursue an objective through multiple steps: obtaining information, reasoning about alternatives, using software tools, communicating with other systems, and initiating actions. Imagine a large project with several specialized agents. A scheduling agent continuously monitors project progress. A cost agent monitors expenditure and forecasts final cost. A risk agent identifies emerging threats. A procurement agent monitors supplies and deliveries. A resource agent evaluates labor and equipment requirements. A quality agent analyzes inspection information. A document agent processes contracts, reports, and technical documentation. Rather than operating independently, these agents could communicate through a multi-agent system. The scheduling agent might identify a potential delay. The resource agent could examine whether additional resources are available. The cost agent could estimate the financial consequences. The risk agent could assess alternative responses. A human project manager could then receive a coordinated recommendation rather than several disconnected reports. This represents a transition from software as a passive management tool towards software as an active participant in project management. Digital project management applications across disciplines. The significance of digital project management extends well beyond construction. In engineering, digital platforms can integrate design, simulation, procurement, manufacturing, and commissioning. In information technology, digital project management can coordinate software development, cybersecurity, cloud migration, and AI implementation. In healthcare, it can support hospital developments, digital health implementations, clinical infrastructure, and research programs. In energy, digital project systems can manage renewable energy, power networks, storage systems and major infrastructure. In manufacturing, digital twins, robotics and IoT can connect project management with production systems. In water and environmental management, digital technologies can support treatment plants, water networks, desalination, recycling and environmental infrastructure. In research and development, AI can support grant projects, research portfolios, resource planning and complex multidisciplinary collaborations. Commercial project management platforms can increasingly connect planning, scheduling, resources, costs, collaboration, analytics and reporting. These systems can then be extended through cloud platforms, APIs, AI, automation and customized programming. Digital project management is therefore becoming a general management capability applicable across almost every industry. Towards intelligent and autonomous project management, the long-term direction is towards intelligent and autonomous project management. The first generation of project software primarily digitized existing manual activities. The next generation connected project information through cloud platforms and integrated databases. The emerging generation adds prediction, optimization, generative AI and AI agents. Future systems could continuously collect information from projects, update digital twins, identify emerging problems, simulate alternatives, optimize responses and recommend or implement selected actions. A possible future architecture is IoT plus computer vision plus robots and drones plus cloud, edge computing plus digital twins plus AI plus optimization plus AI agents plus human leadership. Such systems could continuously answer 5 fundamental questions. What is happening? Why is it happening? What will probably happen next? What is the best response? Which actions can be safely automated? The final question is particularly important. Autonomous project management should not mean removing humans indiscriminately. Major projects involve ethical, contractual, safety, social and strategic responsibilities that require accountability and professional judgment. The more realistic future is likely to be a hierarchy of automation. Routine information processing, monitoring, forecasting and administrative activities may become highly automated. AI agents may manage defined workflows autonomously. High-impact decisions may remain under human approval. Project managers may consequently move away from spending much of their time collecting information and preparing reports towards strategic leadership, judgment, stakeholder management, innovation and supervision of intelligent digital systems. Digitalization is therefore not simply about introducing new software into project management. It represents a fundamental redesign of how projects can be understood, predicted, optimized and delivered. The convergence of advanced project management methods, uncertainty analytics, computer vision, robotics, drones, reality capture, cloud and edge computing, programming, AI-assisted software engineering and multi-agent AI systems creates the foundations for a new generation of project management. The ultimate opportunity is to create project management systems that are increasingly connected, predictive, adaptive, intelligent and selectively autonomous, while retaining human leadership and accountability where they matter most. This transformation has potentially enormous implications for productivity, costs, sustainability, safety, innovation and the successful delivery of the projects upon which modern economies and societies depend. If you enjoyed this discussion, don't forget to subscribe, like, and share. Stay tuned for more insights on AI, quantum computing, and emerging technologies shaping the future of software and humanity.